Last class, we started discussing about the chemical reactions of carbonyl compounds. We encountered two important points there. One, uh, the nucleophilic addition reactions mainly dependent on polarity of the C double bond. Second, it depends upon the crowdiness or bulkiness around the C double bond O group. Okay, and we exercised few examples to understand how the rate variation is observed when it comes to nucleophilic addition reactions. The data is also supporting about how decreasing carbonyl polarity or increasing um, bulkiness is decreasing the rate of nucleophilic reactions. Okay. Then we started discussing about hydration reactions. Okay. When it comes to hydration reactions, I told you that on adding H2O in acidic medium, you will get geminal diols, which is hydrate of aldehydes. Okay, geminal diols as in what? So, in case if you add water molecule to aldehyde, you will get two OH groups on the same carbon. If two OH groups are on the same carbon is present, we call it as a hydrate. And since it is on the same carbon, we use the word geminal diol. This can be seen both in acidic medium as well as basic medium. Okay. And we learned that when it comes to the hydrate forms, all hydrates will be in equilibrium with their respective aldehydes and ketones. But which one will have higher values? For example, formaldehyde, high value. Acetaldehyde, relatively okay. To some extent, still it is towards the product formation. But any form of ketones, right, which are donating in nature, they will be extremely low value. That means they are unstable hydrates. But if there are any withdrawing groups like CCl3 or CF3, the concentration of hydrate increases drastically. For two reasons. One, it is increasing the polarity of C double bond O. Second reason, they are making a strong intramolecular hydrogen bond. So here we have strong intramolecular hydrogen bond. All right. And this is where we stopped. So if you notice that when it comes to intramolecular hydrogen bonding, in the case of cyclopropanone, this is going to be very stable form. And why is it stable? If you make this OH and OH, the sp2 carbon is converting into an sp3 carbon, which will release the strain. Release the strain. So since release the strain, K equilibrium is high. That means the reaction in the forward direction is high. Next, if you notice nin hydride, in the case of nin hydride, after making an uh, hydrate form, you will have O and H here, O and H here, and double bond O and double bond O. So you can notice that there is a hydrogen bonding here as well as there is a hydrogen bonding here. So due to this strong intramolecular hydrogen bonding, again K equilibrium is high. So it is a hydrate of nin hydrate. Hydrate of nin hydrate. Next one. If you have, diphenyl here, diphenyl propane trione, here also you would have like this, where O and H hydrate is forming at the central carbon, where they can show hydrogen bonding with a double bond here, and phenyls will be like this. Now you can see again there is a strong hydrogen bonding established between these two. So here also this is hydrate of, okay, diphenyl propane trione, okay, DPP. So this is also very high K equilibrium value. Okay. So if to be precise on total how many we have, please check. If you were asked the question, you will find out this aldehyde, formaldehyde, acetaldehyde, chloral, floral, This is like bifluoride on both sides. And these five here. And then we have cyclopropane, ninhydrine, and then we will have last one, which is DPP. These are the total 8 compounds that you will have to learn. That's it. Anything other than this will not come in your exams or syllabus. Correct? So learn these 8 hydrate forms which are most stable hydrates. Okay. Next. The second one is about reaction with alcohols. Alcohols, I mean aldehydes, when you react with the alcohols, they will only happen to react when the medium is acidic. That too in a dry form. That means it should not have any water content. I could use a dry HCl here, and in that case, you will see it will start forming hemiacetal form first. Hemiacetal is generally unstable in both acidic and basic medium. Why? If you continue to react hemiacetal also with excess amount of alcohol, it will start forming something called acetal. And this acetal, although it is unstable in acidic medium, it is quite stable in basic medium. This is quite stable in basic medium. Okay. Well, this is the fundamentally this is what we will look into, that being a more stable form, correct? This is what we will look into and make the reaction to happen properly. Check what and how the reaction is happening. Let's see the mechanism. The first step is about aldehyde trying to take H plus, and that will be happening by making CH double bond OH plus. Okay, now CH double bond OH plus makes carbon to have sufficient positive charge. That's when the alcohol will start attacking. Okay, this alcohol will start attacking on this carbon, moving this bond away. So that way you can see the nucleophilic addition reaction is successful. So you will have OH and R with plus charge. And internally, the lone pair present on this oxygen can easily fetch this H plus ion. So as it takes away, we call this as intramolecular proton transfer. By doing so, it will get OH2 plus and OR here. Okay. And eventually, this molecule will push the electrons of oxygen as a lone pair to remove this part. Okay. So here we can say we have RCH double bond OR plus. Okay, sorry. First, let me complete this part here. I'll do this in the second step. Sorry, I'll do this in the second step. First, here, if the concentration of alcohol is not sufficient, that means slowly the H plus will be lost into the solution. Slowly the H plus will be lost into the solution, and we will get this as OH and OR, which is hemiacetal. This is hemiacetal. Okay. But if the concentration of this compound is more, right? The concentration of the compound is more here. So protonation will start happening from this end. Let me show this step here. So H plus as soon as you add it. So first you will get this part here. 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 First you will get this protonated form here. Then intramolecular proton transfer will occur to get this form. And the lone pair from OR will push to get this as RCH double bond OR plus. This is the intermediate which is forming. By the way, this intermediate have a resonating structure as RCH plus and OR this way. This is the resonating structure. So it is like a carbocation is forming here. So then we have CH double bond OR plus charge here. So the second mole of alcohol, ROH, second mole of alcohol will attack here, right? Will attack here, and that will convert into RCH. This bond will move. So that will move towards OR, and OR and H with plus charge. And this will lose out H plus into the solution and convert into RCH, OR, and OR. That is acetal. So hemiacetal and acetal. These are the two forms which you will notice. Here, please check once quickly, everybody. Please check quickly. Done. Please check this. When it comes to ketones, right? Ketones does not form acetals very easily, just like how aldehydes are forming. Okay. But they do react with 1,2-diol systems to form cyclic acetals. Why is that so? Okay. Check out. When it comes to ketones, right? Suppose if you have a ketone, let me show you ketones. Ketones are generally less reactive than aldehydes. On top of that, if you take 2 moles of some alcohol in the presence of dry HCl, okay, in that case, what do we expect this to happen? We will get this as OR and OR. This is the product you will get plus H2O. Now, I want you to understand that the delta H in this case of the reaction is quite less. I mean, it's not very differential form. Okay, or I can say delta H values less negative, very less negative value. So that means this reaction is highly entropy driven, correct? And if you recall, to make the reaction spontaneous, delta G has to be negative. But if this is not accounting much for the spontaneity, then only entropy will account. If entropy is positive, then only delta G will remain negative, correct? So to keep the delta G negative, the entropy has to be positive. But please check in this case, delta S of the reaction is quite negative. Why is that negative? See, the reactant side we have three molecules. On the product side we have only two molecules. So entropy is decreasing. So since entropy is decreasing, this is less spontaneous reaction. Okay. So how do we compensate this entropy factor change? Okay. So as it is, ketones are very less reactive. That's why the delta H release is not sufficient to compensate the T delta as well. Okay. But what we can do, we can start improving the entropy factor. That means try to increase or at least try to neutralize. How do we do this? See, suppose if you have the same keto form, instead of taking 2 moles of alcohol, now I take this as 1 mole of alcohol which is connected in a vicinal form here. So, and then react this with dry HCl. On doing so, now what would I get here? is that we will get a cyclic acetal form here. So this will be a cyclic acetal form, okay, plus H2. So due to the cyclic acetal form here, correct? This is glycol. So due to cyclic acetal form here, this will be very stable form, right? I'll try to keep this as this way. Why? Please check entropy now, entropy of the reaction. Reactant side we have two molecules, product side we have two molecules. So entropy factor is 0. And since delta H of the is less negative, so overall delta G will be negative and the reaction will be spontaneous. So that's how you can increase the spontaneity of the molecule. We can also increase the spontaneity of the molecule even by making a cyclic ketones. So if you take cyclic ketones also, correct, with 2 moles of CH3OH, although entropy is increasing here, because you are taking a cyclic ketones, the reaction is still observed to happen. That means you can still get the uh, acetal form here. So OCH3 and OCH3 is observed. Correct? The product is observed. Product is observed. Okay. Here. So what are the important points we need to understand? First, acetal form acetal form undergoes through nucleophilic addition reaction. Second, carbocation intermediate is formed. Okay. Third factor, when it comes to acetal here, hemiacetal here, like this, we have OH and OR. If you take it in basic medium, OH minus will immediately take the H plus, convert into O minus, and that O minus will push and remove this OR, and that's how it will convert into a keto form plus RO minus. Okay, and on the other side, if you have acetal form and then you react with OH minus, then there is no reaction happening. That's why acetals are stable in basic medium. Okay, so conceptually, everybody, other than the mechanism, these are the pointers you should know. What happens in the case of ketones, what happens in the case of cyclic ketones, and when is it stable. Done? Next, notice intramolecular acetal formation. The rate of intramolecular is even faster. Okay, why? Let's see this with an example. OH is there here, like this. It is connected to double bond O, and here also it is connected to OH. And this, if you treat it in dry HCl, correct? You see the ring size here: 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Two 5-membered rings are formed here. So it is basically O this way, O this way. This is the ring size formed here. Okay. So plus H2 plus H2O. Delta S will be greater than 0. Okay. So by the way, I can write this molecule in this form, or I can write the molecule in the other side of the form. So both of them are one and the same. So if I write it this way with O here, because distance wise they are at the same distance, right? It doesn't matter whether, remember it is a spiroform. Spiroform means how is the structure? The structure is like this. So here it is like, imagine coming out of the plane, and here with the carbon, it is going inside the plane like this. And here it is on the plane. It is on the plane this way. So this is the structure how we. Because this structure does not have any plane of symmetry or center of symmetry, the molecule is chiral. So a lot of times it will be asked like, what about the molecule here? So why? No POS, no COS, and most importantly, no alternative axis of symmetry. Because watching that, it appears as if it has an alternative axis of symmetry, but unfortunately, it does not have any alternative axis of symmetry. Okay, next. Notice if you have this one, in case if you have this one, where we have OH and ketone here like this, okay, and with dry HCl. So with dry HCl, it will make a five-membered ring like this with methyl group here, correct? Sorry, methyl and OH here. So this is also forming a chiral center, single chiral center, but molecule will be racemic mixture. Racemic mixture form, right? So this is hemiacetal. Internally, it will start forming an hemiacetal easily. Got it? See, hemiacetal form is heavily observed even in the case of glucose. See, glucose is a structure like this where you have six carbons. So double bond OH. This is 1, 2, 3, 4, 5, 6. So in glucose, what happens is at every position we have OH2 this way. Every position we have OH. So internally, even when you have it in aqueous solution also, without having dry HCl, even if you have in aqueous solution, because see what is happening, intramolecular attack is very easy because the entropy is drastically increasing. Entropy increasing is always a spontaneous reaction. So even without a catalyst also this will happen. So just put some aqueous solution, the reaction would happen. So what you will notice here is from this fifth carbon position onwards, this OH will attack this carbon, converting into a six-membered ring. Now that six-membered ring actually looks like, you know, a pyrene structure, a six-membered ring with a oxygen. So how do we write that? We write it like this. This is that six-membered ring. Okay. So on this six-membered ring, now I can say that here, if at all I write OH on top here, correct? The next OH is also on top. Next OH is bottom. Next OH is top. And next OH is like this. This is how the molecule is. And the same type of another molecule will also be formed because it is sp2 hybridized. Both are possible. Another form is where this OH is downwards. Okay. In this case, the OH is upwards. In this case, OH is downwards. Okay. Going ahead, we'll learn more in detail about this. As of now, I'll just write down. This is called as alpha glucose. Sorry, this is called as beta glucose. Beta glucose. This is called as alpha glucose form. Okay, one is alpha glucose and beta glucose. See, both of these are diastereomers. Both are diastereomers. Okay, both are hemiacetals. Both are hemiacetals. Okay, now remember hemiacetal diastereomers at carbon 1 position, because if you write the IUPAC numbering also, this is the carbon 1 position, right? At carbon 1 position, where you get a hemiacetal form, that position is called as anomeric carbons. Anomeric carbons. C1 is anomeric carbon, and anomeric carbons make alpha and beta glucose as anomers. We call them as anomers. Just like how we use the word enantiomers, diastereomers. Mesomers. Here we use the word anomers for these two. Clear, everybody? These are called as anomers. More detail about this. There is a complete chapter on it. You know, biomolecules is all about that part only. So learn that. Okay. Clear, everybody? Please ask me if you have any doubt in this case. Check. Check. What are the applications that are used when it comes to acetals and hemiacetals? See, what is the application part here? Applications. See, first application is about having a ketone here this way and an ester here this way. If this is normally reacted with lithium aluminum hydride will reduce on both positions. Ketones also, it will reduce this into alcohols and ethanol. Correct. But what if I do not want to reduce this what do you say? Do not want to reduce this ketone, but I want to only reduce the ester part. Okay. Especially this kind of help, this kind of application where selective reduction is supposed to be done. In that case, this concept of acetal will be very, very helpful. So see how does this help? First, what we do, we take this molecule and react this with dry HCl, dry HCl with glycol. And glycol immediately makes an acetal form here, this way, an acetal form here. And ester would still remain the same, no disturbance on the ester part. And now you react with lithium aluminum hydride. See, usually lithium aluminum hydride is a basic nature. And you know that hemiacetals are not disturbed in any kind of base. So no disturbance will happen on that position. This will still remain the same. But here the reduction will take place. Correct. Furthermore, if you react this with H3O plus, now you know that acetals are unstable in acidic medium. They would get back to the formation of ketone and again glycol will come out here. Correct. And here this OH will be present the way it is. So we will have this as OH. So this is the final product. So you can clearly notice that without disturbing the ketone, we are able to reduce it. Okay. This is also called as locking. Locking that functional group, then we are operating such a way we are able to get this into right. Clear everyone? Right. Check. Now, another way to look at this, another reaction here. Right. So let me show one more application. Suppose if you have acid chloride here like this double bond O, double bond H. Okay. I treat this with glycol in dry HCl. So in that case, no disturbance will happen on acid chloride side, but this direction you will have an hemiacetal form like this. And thereafter, if you react with CH3 excess, CH3 excess, you know that excess MgBr will make the chloride to leave and tertiary formation will be observed here. So you'll get this as O minus and here we'll have O connected this way and here. Okay, and here you'll have MgBr plus. This is a product form. And this on hydrolysis, H3O plus, complete H3O plus. So alcohol will be formed here and this side aldehyde will remain. Okay. glycol will be out. So this is the way you will get the final product. Done. So I hope you guys understood the application part, how it has been asked. Please check. All good. See, next. If ROH is alcohol, then RSH is thioalcohol. If this is glycol, then SH form is thioglycol. So now we are trying to perform a similar reaction with thioglycols. Okay. So for example, if you have an aldehyde RCHO and if you have thioglycol here in the presence of dry HCl, you'll have a very similar reaction RH with a cyclic form here. Sorry, instead of oxygen, now we have sulfur. Sulfur collected this way. Okay. So this is cyclic thioacetal. Cyclic acetal. Cyclic thioacetal. Thiocyclic has a very important advantage. What is that? Please check. Suppose, in case if you have, you know, let's say I have an aldehyde RCH here, and here we have oxygen connected like this. This is an acetal form, cyclic acetal form. Same way, I have one more acetal form here, which is sulfur. Yeah. Let's say there is sulfur and sulfur here. Now the important part is if you compare the acidic strength, okay, if at all I'm comparing the acidic strength here, then this is significantly acidic. Now this acetal is significantly acidic. Why is that? See, if you make a conjugate base of both of them, imagine I make a conjugate base of both of them. Okay, so conjugate base as in H plus has been removed, minus charge will come, minus charge will come. See, sulfur also has lone pairs, oxygen also has lone pairs. Okay, but what is the important part here is this lone pair can make resonance stabilization on both ends because sulfur has empty d orbitals. But here, such kind of resonance does not occur. On the contrary, there will be strong repulsions from the lone pairs here, because of which this becomes extremely stable. The conjugate base is extremely stable, and because of that stability only, this cyclic thioacetal is strongly acidic. So this property would be very, very useful for us whenever you want to assess some reactions here. So let's do this with an example. Okay. So suppose, what is this example? Suppose I have CH3, CH2 and C double bond O plus I have been using SH and SH this way. Okay. So in the presence of dry HCl. Dry HCl. Okay. Sometimes instead of dry HCl, they will also take it as TSOH. Okay. TSOH. Or it will be written like this. Sometimes it is para methyl or para toluene. Okay. Sulfonic acid like this. Complete structure will be written here like this. Correct? This or this. Okay. Here. So this is like PTSA also. PTSA. PTSA as in para-tolide. Okay. This is sulfonic acid. So all of these meant the same thing. Okay. So they all meant the same thing. What will they do? They will first make an hemiacetal form here. So cyclic acetal form, CH3, CH2, CH, and then we'll have S connected this way. Once you get this here, this becomes very essential to remove H plus. So suppose if I use an extremely strong base like B minus and Li plus, our Li is a very strong base. This strong base can easily extract this proton. So as it extracts, we'll get this as CH3, CH2, C minus, C minus, and S connected. This is the compound we have. Okay. Now this compound what we made has a huge advantage. You can make a lot of reactions out of it. What are all the lot of reactions? First, I can make to react this with alkyl halide, something like CH3Cl. So via SN2 mechanism, this carbon can attack here, remove chlorine. So we will get this as CH3, CH2, C with CH3, and the cyclic hemiacetal, cyclic thioacetal will remain the same. Okay. And once you get R and R substitution done, now what we could proceed here is we can react with this HgCl2 in aqueous solution followed by CdCl2. On doing so, hydrolysis would happen here. CH3, CH2. C double bond of CH3 will come. Mercury will completely take the cases of sulfur here. Correct. And this will again come back to the hemiacetal form. Glycol form. Have you noticed something? I started off with propanol. Now I ended up with 2-butanone. So if you want to convert into a desirable ketone, this is one important way of doing it. So from aldehydes, you are converting into a ketone. There are certain in-text questions given in the NCRT, everybody, where the conversion is asked. If ever you were asked to convert an aldehyde into ketone, this is one best method. Okay. Second reaction. See, I could directly make this to react with D2O. I could make this to react with D2O. Correct. On reacting with this D2O, so we can get this as CH3, CH2, CD, sulfur like this. And then on hydrolysis, you'll be able to make this into CH3, CH2, sorry, CH2, C double bond O and D. So that means instead of the original hydrogen here, if you want to replace that with deuterium, this is another method you can follow. Got it? This is another way you can follow. And now notice the case here, whether you have the above case here or below case here. Any of this case, if at all I treat this with Raney nickel or strong reducing agent like H2 nickel and so on. Then what do I get? CH3, CH2, CdCH2 plus SH and SH. Correct. So here, this has converted to an alkane. That means you start with an aldehyde, end up with an alkane. Remember, aldehydes to alkanes, there are two major reactions which we do. One is Clemenson's reduction, the other one is Wolff-Kishner reduction. This is the third one. This is also be used as a uh, reduction to alkanes. And this reduction to alkanes is what we call it as the Mosingos reduction. Mosingos reduction. Okay, so please check. What is the importance of thiol addition? In exams, especially in advanced exam, this is one of the strongest cases where instead of using simple acetals, we always use thioacetals and do. Boys and girls, any doubt?
No, sir.
Ah, beta.
No, sir, I don't have any doubts.
Ah, okay. Right. Let's discuss the next reaction. Reaction with HCN. Okay. How is this reaction working? Let's start. Um, this color here. See, when it comes to HCN, HCN is a very weak acid. Keep that in. Weak acid. Since it's a weak acid, the composition of Cn minus is quite less. Very less quantity. So it has very less quantity of cyanide. That's the reason why we use what we use. We will add KCN, which will ionize completely as K plus and Cn minus. So now this is a good yield, good yield and strong nucleophile. Good yield and strong nucleophile. Okay, clear. So that would help, making the reaction faster. So how does the reaction work? See, R C double bond OH if you react with Cn minus. So this Cn minus first attacks carbon, breaks the bond here. So this is still in equilibrium, mind you. So that will convert into R, CH, O minus and Cn. And this is reacting with Cn. So O minus will easily take H plus, push away Cn minus. So that's how it will convert into R, CH, OH and cyanide. So this is called as cyanohydrin. So what you will notice is a cyanohydrin formation everywhere. Okay. Usually cyanohydrin reactions are often used to express that there is a hydrolysis that can be follow-up reaction. So when you make a hydrolysis, it will convert into OH and COOH, which is a lactic acid basis. So this is called alpha hydroxy acids. Alpha hydroxy acids. And alpha hydroxy acids, generally when you heat it, right, this will become cyclic esters like this R, CH, correct? We will have here oxygen connected with another carbon double bond O. Here also we have CH. Here also we have CH connected with oxygen with a double bond O here and R this way. Okay. These are called cyclic esters or lactides. Lactide. If you have only one ester, it is called lactone. If you have both sides esters, we call it as lactides. So this is a cyclic ester or a lactide formation. Now I'm telling you, this is an extra information for this topic. For this topic, this is extra information. As of now, what you need to know is how the cyanohydrin is formed. Okay, this part from here to here, you will notice again in carboxylic acids. Okay, So I'm writing it just to make you feel that there is an application oriented with cyanohydrin. Okay. Next, once you get a cyanohydrin here, correct. Notice one thing: reaction takes place with all the aldehydes. Reaction takes place with all aldehydes and ketones, except except few. Okay, what are those cases and what are those few? I'll check it out. So if you have any kind of formaldehyde, acetaldehyde, correct, even further matter, tert-butylaldehyde, this one also. Then you have simple ketones or isopropyl ketones here, like this. Or we can have C double bond O methyl ketone here, right? Up to this ketone. Then benzaldehyde, okay? Then benzoketone form. Up to this, they all will give good yield. They all are giving good yield. That is literally almost all of them. Which are not giving good yield or almost stop the reaction. If you have this form or pH, C double bond OPH, we can say there is very poor yield or no reaction. So we can say these two cases will not give you much of a reactions in this case. Got it? Even, sorry, I will put this one also into this category here. These three would hardly give any reactions. Okay? So overlapping with this one. Slightly below here. Done. Let me show you some application of these reactions. Check. If you have CH3CHO and you react this with HCN, see, in reactions only HCN is given, but by default you should understand that there is small amount of casein used to initiate the reaction. Then you will get cyanohydrin form CH3, CHOH, and CN. This is cyanohydrin. If the cyanohydrin is made to hydrolyze, if you hydrolyze this part, you will get this as CH3, CH, and we'll have OH and COOH. What is this one? This is alpha hydroxy propanoic acid. Propanoic acid. Okay. You know, this is nothing but lactic acid, everybody. Okay. So the acid present in the milk is lactic acid. This is the one. Okay. Important application there is making of lactic acid. Second application you see in case if there is any conjugation here like this, an aldehyde with a conjugated form. And when you react with HCN, correct, there are two products you can get. One product is direct addition here with hydrogen here, OH and Cn. Another form of addition here is, this double bond O will be like this, and here we have Cn. Okay, this is called 1,2 addition. This is called 1,2 addition, and this is called 1,4 addition. This is called 1,4 addition. So both products are possible. Now let us understand how the 1,2 products and 1,4 products are coming into picture. Check. Suppose if you have this ketone here like this, and Cn minus notices that this is also a position where I can attack, pushing this bond. This will get O minus. And when it gets O minus, it can react with this HCN. It can react with this HCN, making into, a cyanide here, a CN here with a double bond here, and OH here. So what are we getting? Hemiacetal form. Sorry, this is enol form. So you're getting an enol form. And enol will tautomerize back into product formation as double bond OH. Okay, and cyanide. Notice one thing, this CN got added here, hydrogen got added here. So if I read the position, it is like this is 1, this is 2, this is 3, and oxygen is 4. So what has happened? It has happened to be 1,4 addition. That's why we call it as 1,4 addition. 1,4 addition, and that 1,4 addition will convert into this ketone. Okay, ketone or RDA. So this is how 1,4 addition works. 1,2 addition is a regular case which we have noticed already. See, now 1,4 addition and 1,2 addition are subject to temperature. Okay, let me write down that. At low temperatures, that is 0 degrees all the way to minus 40 degrees like this, correct? Then 1,2 addition, 1,2 addition are favorable, okay, and major product. And those products are called as kinetically favored product or kinetic favored. KCP, kinetically controlled. At high temperature, at high temperature, that includes anywhere from 10 degrees Celsius towards 80 degrees Celsius like this. Then 1,4 addition, 1,4 addition are favorable and major. Favorable and major. So this is thermodynamically favored, which we call it as TCP. Okay. So depending on the temperature, students, you have to manage accordingly. So based on temperature, identify the major and minor product in this case. Got it? Now, in case if you strictly want to get, here I have written it, see, if you want to strictly get 1,2 addition product only, then instead of taking HCl, you take this as trimethylsilyl cyanide. Trimethylsilyl cyanide is a weaker nucleophile which will only allow to attack on 1,2 positions and not in 1,4 positions. Got it? So to increase the 1,2 content and do not want to depend on temperature, then trimethylsilyl cyanide is a better form, and then do hydrolysis instead of HCl. So all the HCl reactions are clear, everybody? Okay. Right. See. Next, if you react with NaHSO3, NaHSO3, what is the reaction? First, notice what is the structure here. So O double bond S, then O minus Na plus OH, and a lone pair present on sulfur. This is sodium hydrogen sulfate. Sodium hydrogen sulfate. Okay. So example, if you notice, aldehyde, when you react with HSO3 minus Na plus, that would be in equilibrium to get this as RCH, O minus, and SO3 minus. Got it? Sorry, HSO3 minus, SO3H. Okay. And that will take away, that is intramolecular proton transfer will take place and convert that into RCH, OH, and SO3 minus Na plus. Here also write Na plus. This is how the reaction takes place. Okay. I mean, if you notice the mechanism, it's simple. So all you need to have is the aldehyde here, C double bond OH, and the lone pair present on the sulfur will be the attacking species like this. Okay, O minus and OH. So this lone pair will attack. This bond will close. It will open from the other end. As that happens, you will see you'll get this as RCHO minus, and on the sulfate also we will have, since it is connecting from sulfur end, we will have this as O minus, double bond O, and OH here. Got it? OH here. Ouch. Sorry. Sorry. Check. So sulfur is getting a positive charge here because it is donating that case. Okay. So that makes this group as double bond O. So that means it will convert into a formation of R C H O minus S double bond O S double bond O and OH like a sulfonic acid. Sulfonic acid problem here is we have internal acid base reaction. So that will make this as RCH OH here and SO3 minus, and since sodium is present in the solution, so this would appear like a white PPT. It will appear like a white precipitate. So that's how you will get this white precipitate form. Okay. What are the important points to be learned here? All aldehydes, all aldehydes give positive sodium bisulfate test, and only methyl ketones give positive sodium test except except PHCOCH3. This is methyl ketone, but it will not give positive test. Or tertibutyl COCH3. This will not give positive test. Okay, so these two will not give any positive test at all. Now, other than that, rest all will not give positive test. So let me write down here compounds which does not give positive test. Positive test. Correct. So which of them will not give positive test? Even the ketone is ethyl on both sides, no positive test. Okay. If you have anything like this, also no positive test. Correct. If you have a phenyl and ethyl on the other side, no positive test. Okay. And if you have phenyl and phenyl, definitely no. Phenyl and phenyl, definitely no. Tert-butyl and ethyl or methyl or any tert-butyl, definitely no. These are the ones. And the ones which I already mentioned, even though there is a methyl form, still no. Even though methyl form on this section, still no. These are the ones which will not give positive test. Rest all the regular aldehydes and ketones, they all will give you, I mean methyl ketones, they all will give you positive test. Okay. Second important point about this is, see, if you notice that RCHO minus Na plus and SO3, sorry, OH and SO3 minus and Na plus. This is the white PPT. Now this white PPT, if you subject to acidic medium here, acidic hydrolysis. On acidic hydrolysis, this molecule will again come back into aldehyde, just like acetal form. This also get dissolved and converted into an aldehyde form and separate that as SO3 minus H2SO3. It will convert into H2SO3. Okay. This is a technique that we can use. What is that technique? Okay. Used for purification, purification of purification or separation of aldehydes from alcohols. So usually whenever there is aldehydes and alcohols together, like in this case, CH3 CHO is there and CH3 CH2OH, ethanol is also there. These two are miscible. That means they can easily mix and they can exist as a mixture. So now if I take this mixture and react this with sodium bisulfate, NaHSO3 with sodium bisulfate. What do we get? We'll get this as CH3, CHOH, and SO3 minus Na plus. This forms a PPT, but alcohol remains the same. Alcohol does not have any impact. Okay, liquid only. Since it is liquid only, we can use filtration process and remove this out. Okay. So what do we have? We have a PPT form separated and filtrate separated. PPT form will have this one, correct? PPT form will be this one, and filtrate will be this one. Filtrate will be this one, correct? This is the filtrate form, this is the PPT form. And now, after separation, again, what you can do? You can simply do hydrolysis, acidic hydrolysis now. On acidic hydrolysis, even this will get dissolved again and convert back to aldehyde here, correct? This aldehyde here plus H2SO3. So that's how we can separate these two. Clear? So quickly go through entire reaction set of sodium bisulfate. I'll give you a minute's time. Please check. See the next reaction set. The next reaction is reaction with ammonia derivatives. Okay. See, this is ammonia. If you remove one hydrogen, replace that with some group Z, any group Z, then that become ammonia derivative. So if we take any ketone or aldehyde, react with the derivative, what do we expect is that a dehydration, that is H2 and O together will leave and you'll make this as a double bond NZ. Okay, and usually once you make a bond this way, most of the cases they are crystalline solids. Okay, so since they are crystalline solids, it is easy to separate it out acid. Okay. So check it out. And this is typically used as a test for identifying the aldehyde or ketones. Right. So let me show you the reaction, how it is working. So if you have C double bond OH aldehyde plus H2N present with Z, or let me write down this way, H and H present with Z here. So what you need to do is simply dehydrate this. So remove this part. So as you remove this part, it will be in equilibrium to get R, H, double bond N and Z. Because there is a lone pair here, it can show geometrical isomers. Okay, it can show geometrical isomers. Now that depends upon how the Z group, how the H group and the other group are aligned to each other. So if the Z group is on this end and lone pair is here, then based on hydrogen and this lone pair group, we call it as a syn form. Okay, sorry. sorry, based on this and Z group, we call it as an anti-form. And here H and Z, if they are on the same side, we call it as syn isomer. So syn and anti-isomers are possible. Okay. And now, what is the mechanism that is happening? Simple. If you have R, C double bond O, H, the lone pair present on nitrogen, which has NH2 connected with some Z group here, that lone pair will attack here, remove this part. But the problem here is the ammonia attack here is not that easy because it does not have any charge. It is like a neutral nucleophile. To facilitate this, what do? We add the group in slightly acidic medium. Because of that acidic medium, the lone pair present on hydrogen will also take this H plus and get into an addition mode. You will get an addition reaction here where you will get CH, OH, and NH2Z with plus charge. So now the lone pair present on this oxygen will take away H plus from here and that will convert into R CH OH2 plus and NHZ here. So again, the lone pair present on this nitrogen will be pushed. That will be removing out the water out of it and convert into RCH double bond NHZ with plus charge. And removing that hydrogen from there, correct, converts that into RCH double bond N and Z. This is a final product form. Please check the mechanism, everybody, how it is happening. So it is happening through an addition reaction first, and after addition, it is undergoing an elimination. So addition followed by elimination. This is the overall reaction. Clear? So what did you notice here is this one, where we have this group is at sp2 hybridization. This group now has become sp3 hybridization. Okay. And again, this has finally become sp hybridization, sp2 hybridization after the reaction. Such mechanism where basically all we are doing is removing the double bond and bringing that nitrogen here, correct? Overall, what we are doing is like, addition and then elimination, right? But what is happening? It is like, sorry, nucleophilic addition reaction followed by elimination. It is like followed by elimination reaction. Got it? Check what are the types of reactions happening. First, aldehyde, when you react with NH2OH, okay, hydroxylamine. In hydroxylamine, you would notice that this OH group will remain and this H2 and O group will be removed out. Now, before going that, sorry, let me tell you, I told you that there is a small amount of H plus required to make this reaction happen, which means the pH that ideally needs to be maintained is anywhere between 4 to 5. This is the optimal pH. So for all these reactions, a mild acidic condition is essential so that the reaction can proceed properly. Okay. So keeping that same mild pH 4 to 5, so you will be able to remove this H2 and O and connect together to convert into an oxide. And I told you like they are usually crystals, they can easily be crystallized and most of them are colored. Same goes with hydrazine also. This H2 and O will go away, convert into this double bond N and H2. Now, this is called as hydrazine, right? Now, notice this one. Whenever a terminology like zine or ine is present, ine, okay? Ine, after the product formation, they will become own. Ine will become own. Okay, so same is the case here. Instead of taking only NH2, I'm taking now PHNH. So that becomes phenyl hydrazine. So again, ine, the product will become own, phenyl hydrazine. Here, same thing. This entire thing is like the replacement for this NH2. So this is called as semi-carbazide. Okay. Again, whether it is ine or ide, this is ide, that will become own. So if this is the semi-carbazide, this will become semi-carbazone. This will become semi-carbazone. Next one, 2,4-DNP test. 2,4-DNP, if you notice, that is dinitrophenyl hydrazine. Again, if you notice the ine form here, that can be converted to an own form, zone, hydrazone. Okay, 2,4-DNP. And 2,4-DNP is the important test for identification of aldehydes and ketones. Correct. This is the official test for official test for detecting aldehydes or keto group, because it will always give you colored crystals. You will get colored crystals here. Okay. Now listen up. This is called as 2,4-DNP test. The test name is 2,4-DNP. Test name is 2,4-DNP test. The reagent name, this 2,4, this dinitrophenyl hydrazine, the reagent's name is called as Brady's reagent. Brady's reagent. It's called Brady's reagent. Similarly, if you have to go aldehyde reacting with primary amine, so this H2 and O can be released and convert that into imine form. That is into imine form. Correct. So if R dash is the phenyl, we call it as the Schiff base. So this is an imine form and N-alkyl imine. So let me write down that part as well. So if you have RCH double bond NH, this family of compound is called as imine. And in case if you have any substituted on this one as some R dash, then we say N-alkyl imine. This is called as N-alkyl imine. This is a completely different family of compounds. Okay. Next, in case if you have a ketone and you react that with 2-degree amine, okay, in case of 2-degree amine, then instead of getting that as a double bond at carbon nitrogen, you will get double bond at the adjacent carbon and you call it as enamine. This is called as enamine. Let me show you how the enamine looks like. Okay. How does the enamine looks like? So basically, you need to understand like this, that when you have RCH2 CHO, you know that this can be written in terms of an enol form as CH double bond CHOH. This is the tautomerization. So imagine it got tautomerized to get this. And this tautomerized form, when you react with H, N and R dash twice, then this OH and H can be released out. That converts into R, CH, double bond CH with N, R2 dash. Okay. So this is ene and amine. So that is why enamine. Correct. So unlike the dehydration of aldehyde happening directly, here it will take the H plus from the adjacent carbon, That will be released out and then nitrogen will get connected. Okay, got it? Right. See, I told you the generic mechanism again. I'll just add that here. Where is it? Here. This is the generic mechanism which I showed you. I'll just add that here just to give you an idea about what is the type of mechanism. Right. So this is the type of mechanism which is happening, correct? Now, in this case, have you noticed that sp2 is converting into sp3? And then again the group has left and this is the so this type of mechanism where initially addition happened and then elimination has happened. Overall, it went for a substitution. That's what it is called as SNTD mechanism. SNTD means a tetrahedral intermediate formation. So you can notice that there is a tetrahedral intermediate which is forming in the middle. Okay, and then you are getting this product form, correct? And it is followed via addition and elimination. Hence, the mechanism can also be called as SN, a substitution kind where addition elimination is followed. So SNAE or SNTD. If you see these two terms, you should understand that we are processing via addition followed by elimination. Guys, I hope you understood the mechanism part and what are all the reactions that are happening with ammonia derivative. Okay. Now, see some special cases of ammonia derivative. Suppose if you have aldehyde reacting with oxime, hydroxyl amine, it will give the product as oxime. Oxime is also a different family of compound. Because it is derived from aldehyde, we call it as aldoxime. But if at all it is derived from ketone, we call it as ketoxime. Okay, and both of them are generally white color solids. Aldoximes and ketoximes are white color solids. Done. Next. C double bond O with NH2 NH2. If you compare this oxygen and this H2 can be released out. So you will get this as C double bond N and NH2 form. Okay. So this is hydrazone. Correct. We learned this as hydrazone. But what if I have the same hydrazone with excess amount of ketone? So that's this NH2 can attack on the other side also and convert into dihydrazone. So remember, if two moles are given, so this is first mole and this is second mole. So if in the reaction two moles are given, you would report this as a product. Okay, you would report this as a product. Next. Next one is thalaldehyde. Next one is thalaldehyde. So this is an aldehyde, this is an aldehyde, this is thalaldehyde. In thalaldehyde, if NH2 reacts here, the second NH2 will react here. And see, both of them are forming an imine form on both ends. You will get a double bond like this. Got it? Got it. So it is like a hydrazone, but thalic hydrazone. So it is called thalhydrazone. Thalhydrazone. Aldehydrazone. Next. I told you this line already. 2,4-DNP test is also 2,4-DNP reagent is also called as Brady's reagent. It is used for detection of carbonyl compounds. 2,4-DNP hydrogens generally would be identified as yellow, orange, red color crystals. Okay, this is not called this is called colored crystals. Colored crystals. Okay, this is very important. See, when it comes to enamine is highly unstable form. Everybody, because imine forms are highly unstable form. Okay, nitrogen having just one hydrogen that get easily hydrolyzed. That means if even small content of water is present, like this, let me show you the reverse mechanism. RCH double bond NH. Okay. Water can easily attack on the carbon here, pushing this nitrogen lone pair. That gives you RCH OH2 plus and NH minus. This NH minus can take H plus easily, convert into RCH, OH, and NH2. That makes a quick pushing off from this lone pair to remove this NH2 and converts that into RCH double bond OH plus. This NH2 minus will take H plus and convert that into aldehyde plus ammonia. So in short, from ammonia, if you want to form an imine, it's easy, but at the same time, imines get easily hydrolyzed to get aldehydes. In lot of mechanism, in lot of questions going ahead, you would notice this happening. That means we will try to make an imine, and then the minute we make an imine, then in one or two steps we do hydrolysis to retain back the aldehyde. Okay, yeah. So since if you have a formaldehyde, this will form an extremely unstable imine. What is the unstable imine that it forms? That is CH double bond NH. This is even more unstable. That is CH2. Sorry, CH2 double bond this one. So it is a highly unstable imine. So this unstable imine, everybody, will make us direct. I mean, keep on reacting multiple number of times. Okay, correct. And that converts into a new compound called urotropine. Urotropine has hexamethylene tetraamine. The structure will be like this. So there are four amines here. I mean four nitrogens here. Between every two nitrogens, there is one methyl group. That's how it gets connected. And this is the structure of tetramethyl amine. Got it? Everybody understood how it is forming? Well, I'll just give you a glimpse of mechanism how that can take place here. Okay, whenever you have urotropine, how you need to think about it. Okay, so I'll do one thing. Yeah, I'll write it down here how the mechanism works. Although urotropine mechanism is not easily asked, just remember it, what might be happening. That's all. Okay, right. So basically, first we got this as CH2O plus NH3. These two, as we reacted, we got the product as CH2NH. Correct? This is the first product we got. Now you process this to another mole of NH3. So what would happen here is we'll get this as CH2 and one side we'll get NH2, another side also we'll get NH2. Again you react with CH2N2. Again you react with CH2NH. So once you get this, you remember that on this position, these two nitrogens, I mean, this nitrogen can again get connected to attach. So this end you open it, NH2 and this CH2. And this NH now got connected to that CH2 and this has become NH2. So this is the second product form. Okay. Imagine this is being done with another CH2NH. So this end will again make the same connection here. So we'll get this as NH2, NH, and NH, and one more CH2 will come and NH2 will come here. Okay. So up to this form it is clear. right? Now, once you get this form here, see the ring size. What is the ring size here? Okay, check out the ring size. 1, 2, 3, 4, 5, 6, 7. Okay, which means if I remove one ammonia, that will make a better ring size. So, which means the lone pair from here would try to attack onto this carbon, removing this ammonia form. Okay, so in that case, what do I get? I'll make a three-membered ring, six-membered ring like this with sorry, NH, NH, and NH like this. Okay, this is a compound which you will get. And let it react again with CH2NH, one more mole here. And as it reacts on this side, NH, NH here, NH here, like this. And this N will convert into formation of, NH2, again NH2 here. So this is the way it get connected. Let it do one more time with CH2, NH2 here. So that happens to increase the ring size here also. So we will get this as NH2 and N connected with this N and NH2. And here we have NH connected like this. Notice again we made a six-membered ring in this case. So what is a six-membered ring? 1, 2, 3, 4, 5, 6, 7. So again if I react with from this position to this position, ammonia will come out, a ring will form. Another six-membered ring will form. Okay. So from here, one more six-membered ring will form here. Got it. So we'll get this as NH like this, N connection here with N this way, and from here we got one more connection to NH and this way. These are the two connections we got. All right. React with one more mole of CH3N2 here. Correct. This time, as we does, we can see CH2 here. Sorry, CH2NH. So make that connection here on this position or this position. Any position is fine. So we will get this as NCH2 and NH2, and that is connected to already existing nitrogen here, which has a methyl group here, and also nitrogen here, NH, which has a methyl group here. Now again you can see the ring size here 1, 2, 3, 4, 5, 6, 7. That means lone pair from here can connect here. So that gives you one more ring form. So N here, N here, like this, N here, N here, and N here. This is the connection. This is urotropine activity. Please check this out quickly. Check one very important application of urotropine, everybody. The urotropine, another way of writing the urotropine is like this also. Suppose if you have, n-membered, uh, if you have like this, you have, that this is a six-membered ring. So in that six-membered ring, okay, in case if at all I remove these positions as nitrogens here, so like this three positions, and put them as N, N, and N. So they all will be connected to one more nitrogen through methyl groups like this. So this is urotropine as well, by the way. This is urotropine. Interestingly, when it comes to urotropine, you react this with concentrated uh, HNO3, HNO3. Okay, so it will take at least 3 moles, correct, and make this into a ring like this with nitrogen, nitrogen, and nitrogen here this way, correct, and you will get these positions as NO2, NO2, and NO2. Okay, so you might wonder, sir, this has all happened with this ring, correct? So what happened to the other rings here? So this entire nitrogen group has gone out, and these three positions nitration has happened. Okay, so this entire carbon with nitrogen and this carbon with nitrogen, all of them will be leaving out as carbon dioxide and NO2. Eventually, you will get this as a final product. This product is called as cyclonite, cyclonite, which is the alternative name for RDX. So this is a preparation of RDX. What is RDX means? Research and developed, research and developed explosive. I'm sure you may have heard about this word RDX. So this is that RDX. So that's an important application of urotropine. Okay. Right, guys, we'll stop.